comma, 4R, and then 2,4 octadiol. Right? And then we have, for the second one, we have the same one. 2S, 4R, 2,4 octadiol. So you remember the S, what was that? E and Z configuration from chapter number 6. We studied about E and Z configuration. So basically E and Z configuration, like in a chain, if the constituents are attached to two different carbons in opposing sides, that would be a Z configuration. If they are attached to the same side, that is an E configuration. E versus Z. So basically what is 2S, which means and carbon number 2 on the right side, and then on the left side, and then in carbon number 4 on the right side, 2,4 octadiol. Well, diol means two alcohols, all mean alcohol, di two alcohols we have in carbon number 2 and carbon number 4. But let me see what's going on here. 2R for 1, 2, 3, 4. 1. Yes. 2S. 4S. 2R. Well, I will explain the enantiomer part and diastereomere part of it. I'll come back to this. We will go back to our slide, and see what's going on there. So basically enantiomer, as I told you, it is like the full negative of a molecule, and diastereomere is the half negative of a molecule. So full negative, if it is 2S, 4R, so they both should be flipped. So 2S should be converted to 2R, 4R should be converted to 4S. This is a complete flip from head to toe. So that's why this is enantiomer. And then the same is happening here, 2S to 2R, and then 4S from the left is converted to 4R, which is also enantiomer. Now, what is diastereomere? So as we go and compare these two, this is 2S, 4R, 2S, 4S. So first part, 2S stays the same, but 4R gets that image on the mirror, because from the right side it is flipped, the molecule is transformed to the left side. So if you compare this to this, we have diastromere. Right? And at the same time, we have 2R4S here. Carbon number 2 has the constituents or the group on its right. Carbon number 4 has the residual group on the left. Here, the first part, 2R and 2R, stays the same, but the second half of the molecule has the image of it. So that's why this molecule, again, as compared to this molecule, is the diastromere. So diastromere is like that half negative, half picture of the molecule, but if it is a full negative, full picture from head to toe, that is enantiomer. So again, 2s4r is the enantiomer for 2r4s. Everything gets flipped, every residual. And again, this is enantiomer to this, but when we compare the two sets together, the first one, 2s4r, if it is converted to 2s4s, that is the diastromere. And if 2r4s is converted to 2r4r, that's also diastromere. So this is how you differentiate between enantiomer and diastromere. But it is confusing me. Now I don't know if you have the answer for it or not, because the drawing doesn't match here. We have on the second carbon, we have the hydroxyl group on the left, which is okay according to this structure. But on the fourth carbon, we have the hydroxyl group again on the left, but it is marked as right, which I feel is not okay. It should be here. I will go and figure out about this. Let me draw another one. So we have the first carbon, the second carbon, the third carbon, the fourth carbon, and then we have the hydrogen, and this carbon is attached to a group of C4H9. So this would be the first carbon, the second carbon, the third carbon, the fourth carbon, and then the rest part of it. Since it is diol, we have two hydroxyl or alcoholic group. The first one is 2s. S, if you draw this symmetric line here, so everything this side would be left, everything this side would be right. So on the second carbon, we have it on the left, because senesciter in Latin is the left, the meaning for the left. So here, the hydroxyl group should be here, right? But when it comes to fourth carbon, it should be on the right, which means I have to write this residual on the left, C4H9, and then here I have to illustrate the hydroxyl group. So then I would say 2s, right, 2s, and then 4r on the right side, 4r, and then I will continue by writing 2,4 octane, because we have 1, 2, 3, 4 plus 4 is 8, 8 is octane, octa, and then we have two hydroxyl group that would be di and ol, 2,4-diol. This seems right to me, but I'm going to see what's wrong with that. 2,4, 2s, 4r, 2,4-octanodiol. And this would be applicable to all the four molecules. Is it Clear or not? Any question with this? No? Okay. Again, I will do this example as well. For example, let's say it's 2R, 4R. With basically, this is the line of symmetry. This would be right, this would be left. We indicate left by S, R by R, right? In Latin. So if we say 2R, which means the hydroxyl group is on the right, on the second carbon, because it is the first carbon, it is the second carbon, which is okay. But when we reach here, again, it should be on the right. So this group needs to be here, instead C4H9. So that's how we can make 2R, 4R, 2,4-octanidiol out of this molecule as well. So I will go again and double check that. I'll see what's wrong. Now, moving to question number 3. Assign CIP, which is Kahn, Engel, Krylov priorities to the following sets of substituents. This is another story by itself, but what is Kahn, Engel, Krylov priority? So what that means is basically the atoms with higher atomic weight, they are prioritized, and when we start naming the molecules, we start with the higher molecular weights. So according to CIP nomenclature, halogens takes the first place, and then it is followed by oxygen, then by nitrogen, then by carbon, and then by hydrogen. And then within halogens, the ones on the bottom comes first. For example, iodine is first, bromine is second, chlorine is third, fluorine is, but they all are prior to oxygen. Oxygen is prior to nitrogen, nitrogen is prior to carbon, and carbon isn't prior to hydrogen. So it follows, because the atomic weight of fluorine is more than oxygen, because it's group 9. The oxygen's atomic weight is more than nitrogen, nitrogen then more than carbon, carbon then hydrogen. This is the order that they follow. When we face these molecules, when we do the nomenclature, we start with the atoms which are higher in their molecular weight. And how? Let's apply that. For example, in option number A, and there's one more rule. If we see a double bond, it is similar to two single bonds with the same atom. So when we talk about CH, double bond CH2, basically this is the first carbon that we start with. It is connected to maybe another one, but this is the radical itself. We are asked to compare the priority between 1, 2, 3, 4 options. So let me break that down. What you can make out of this is a carbon, a radical carbon. It has a hydrogen, it has two more carbons. When you break this, so one carbon comes here, one carbon comes here. This is what basically, when you start prioritizing, that's what it means. They attach to another carbon with another carbon here, and then with a hydrogen. So our target carbon is this one with the star. This is the first option. Now we are comparing this radical to the next radical carbon with one hydrogen, and then with two methyl groups, CH3, repeated two times. CH3 here, CH3 here. Now, the third one is a carbon attached to the three CH3s, three methyl groups, CH3, CH3, CH3. The final one, it has two hydrogens, and only one single methyl group. So we are targeting the carbon which has connection with the subsequent, for example, molecule. Now, as you see here, this carbon is connected to two carbons and one hydrogen. This carbon is connected to two carbons and one hydrogen. This carbon is connected to three carbons, no hydrogen. This carbon is connected to only one carbon with two hydrogens. Now, according to the rule, the CIP rule, Conen-Gold-Prelog rule, there is no halogen in all these four options. So we got rid of that. There is no oxygen, we got rid of that too. There is no nitrogen, that's done. Now it comes between carbon and hydrogen. Now the prioritized radical among the four is the carbon which is attached to the most number of carbons. So in this case, this would basically be the first, and then these two options, it is connected to two carbons, it is connected to two carbons. Now one would think by first glance that they both could be equal, but they are not equal because the second carbon here is loaded with another carbon which has the priority. Instead of that, here it has three hydrogens. So it would be the second, when it comes to nomenclature, the second priority. It would then be the third, and then since it's only connected to one carbon, it would be the fourth. So this is how it goes. Now let's see here. As we see, carbon with the three carbons is the first, it has the highest priority, and then carbon connected to with a double bond to another carbon by breaking this carbon. Basically, we are telling that there is one carbon more here, one more carbon here. So it's the second priority, and then it has two carbons, and it has only one carbon. So it would be the lowest priority. This is how it works, basically. So from the highest to the lowest. And now coming to option number B, this molecule has this radical group, basically, because it needs to be connected to a molecule. Has the first or the highest priority, and then second, third, fourth. Let us see why this is first. So basically, we are interested with this carbon, right? and there is another carbon, there is another carbon. So if we break this bond, it will be connected to another carbon, and the same, this will be connected to another carbon. So the target carbon is connected to 1, 2, 3 carbons, and then each of those carbons are connected to other carbons. That's what basically gives this radical this strength, because it is loaded with all the carbons, right? And then if you break this bond, you are adding basically 2 more carbons. If you are breaking this bond, you are adding 2 more carbons here. So it is loaded with 1, 2, 3 carbons, and then the third carbon is loaded with 2 more carbons. That's why it is the second one. And here, basically, it means 1 carbon is here, 1 carbon is here, and 1 carbon is here, right? It is loaded with 3 carbons, simple. And the third carbon is not loaded with more carbons. And here, as we break this, we will get 1 carbon here, 1 carbon here, right? So because the double bond is the same as 2 more bonds. That's why it is only loaded with 2 carbons directly, 1 and 2, and 1 carbon indirectly. So it has the lowest number of carbons attached to it. That's why it is it happens in the lowest when it comes to the priority as compared to the rest in this. But as we go to example numbers, option number C, in option number C, what's happening is we have oxygen now. As you know, oxygen has a higher atomic number as compared to carbon, because oxygen, you know, they are very close to the 7th group. It is the 6th group element. Carbon is the 4th group element. So it has the higher atomic weight. It has always the priority. So here by CO2, if I go to the details of the structure, it has a double bond with 1 oxygen, single bond with the next oxygen, because there are 2 oxygens. And this oxygen is attached to the methyl group, CH3, right? And now let me compare this to this one. Here we have 1 carbon, and then attached to only 1 oxygen, which is then attached to a methyl group. So as you see, this carbon is loaded by 2 oxygens, right? And this carbon is only loaded by 1 oxygen. That's why it has priority. And then coming to the details of this molecule, we have 1 carbon attached to 2 hydrogens, and then attached to 1 oxygen, and then attached to 1 methyl group, right? So here we have this single bond with the oxygen. Here we have, in both of these cases, we have 1 oxygen. Basically, so since there is those 2 hydrogens making, increasing the number of bonds to 4, if we use the oxygen this way, we still would have 2 remaining unloaded bonds there. So that's why single bond doesn't work here. So CH3 should be directly connected to carbon, and there should be a double bond with oxygen, right? So what that means is we have an oxygen with a double bond, which basically means that when we have double bond, you know that rule, that you break one of the bonds and connect both the molecules to another carbon in order to know the priority level. So in this case, this carbon is loaded by 1 carbon, one carbon here, 1 carbon here, 2 carbons and 1 oxygen, basically. So that's why, although we have 2 hydrogens here, the oxygen-wise they are connected to the same number of oxygens, but this has the priority because of that double bond, and hydrogen is in the lowest priority, so that's why it wouldn't be counted when it comes to compare this the carbon loaded with 2 hydrogens with the carbon loaded with 2 carbons and 1 oxygen. So it becomes prior. And then finally coming to the last one, CH2, which means 2 hydrogens, and then CH3. So as you see here, we have no oxygen here. That's why it is the lowest in the list, because oxygen has priority over carbon from the atomic from the table we know, but because the atomic number is higher. And then when it comes to halogens, we know that halogens are the strongest in the priority that I just draw. So the bromine is the first, and then comes the carbon, which is attached to bromine and two hydrogens, and then a carbon which is attached to nitrogen, because nitrogen is weaker than bromine. It comes after that, and then it comes to a carbon attached to two hydrogens and to one carbon which is still attached to two hydrogens and to another bromine. Although we have bromine here, why it is down the list? Because the bromine is not directly attached to the target carbon, which is the carbon which is connected to the mother chain. So that's why it is the lowest, because bromine is not directly attached to our target carbon. It has an indirect connection with the target carbon. That's why it is down the list. And bromine, which is directly attached, it has the highest priority. Any question with respect to this? No question? You? No? Okay. All right. And then, going to the last question, we are asked that how many stereoisomers of 2,4-dibromo-3-chloropentane are there. Draw them and indicate which are optically active. Optically active, you remember we talked about chirality. A chiral molecule is active versus a achiral molecule which is not optically active. It doesn't rotate from that, the experiment that we talked about last week. So there was that tube filled with the solution of this molecule, and at the one end you project the light. If the light gets rotated by the other end, it means that the solution inside the tube is chiral. If the light is not rotated, then that molecule is called achiral. So we are asked here to draw different isomers, stereoisomers, and to say which ones are chiral and which ones are not chiral. So as we go and see here, there are 4 stereoisomers of 2-dibromo-3-chloropentane. C and D, which are these ones, are enantiomers and are optically active. Why they are active? Because the bromine are on different sides, which makes the molecule chiral, and it rotates the light. Here, in carbon number 2 and carbon number 4, we have bromines to the opposite sides, right? So that's why it is chiral. But when it comes to the first and second one, bromines are on the same side, bromine on the same side. Chlorine can be on the same side or on the opposite side. But anyways, these two are achiral. Why? Because they do not rotate the light, because the bromines are on the same side. The light is not polarized. The light can easily pass through it without being diverted. But in these two cases, the lights would be diverted. So basically, we have 4 stereoisomers of 2,4-dibromo-3-chloropentane. Any questions so far? All right. So in our last session, we talked about organohalides. We talked about how what are some of the properties of organohalides, and then we talked about how reactive they are because of that electronegativity that is present in 7-group atoms, iodine, fluorine, chlorine, bromine. We talked that they are so reactive, and once they become in contact with other molecules, they start the reaction. And even with alkanes, which are not so much reactive, they are able to replace the hydrogen and react with them. Today we are focusing on two specific types of reactions that are carried out by organohalides or alkyl halides. And one of these reactions is called substitution. The other of the two reactions is called elimination. So the halides, they can easily, when they become in contact with other molecules, organic molecules, they easily carry out this type of reaction which is called substitution, or the next one which is called elimination. Now, what does substitution look like and what does elimination look like? In a substitution, for example, you have a meta-eta, ethyl bromide, right? So it is that alkyl halide. Alkyl halide, for example, if it in the environment, if we have enough hydroxyl groups, free hydroxyl groups, substitution means that the bromine is substituted by that, and bromine is released after the reaction. So hydroxyl group, because it has a negative charge, which means that it has the electron to share. Now we know that what's going on between carbon and bromine is the electron pair wise, because bromine has a more electronegativity power. That's why the pair of electron in this bond is much closer to bromine, and carbon is not happy with that situation. Carbon almost feels lack of hydrogen in this bond. So whatever other molecule or group or atom that has the tendency to share electron more fairly than bromine, carbon is detached from bromine, and bromine becomes happy too, because it says, okay, now I got the pair of electron for myself only. This is what basically electronegativity means. And then hydroxyl group comes and then make a bond with the carbon here, as you see. So it is basically the substitution which is happening. And then elimination happens, for example, if there is another, catalyzer which should promote the hydroxyl and hydrogen reaction. So hydroxyl would make water with the hydrogen and then would leave that bond free. That bond again brings that pair of electron more fairly and shares it with the next carbon than bromine. So that's why the bond gets attached to the next carbon, making a double bond and releasing the bromine. Bromine, because of its strength in grabbing the pair of electron, is easily released from this bond. So here, basically, as we see, the halogen is eliminated completely. It's not substituted by another molecule. It is eliminated, and then the double bond between the carbon is formed. So that's why this category of reaction is called elimination. Basically, all the times we have substitution or elimination. Now, there is this next question: when would substitution happen and when would elimination happen? So basically, this is answered by the type of the base that the molecule, this alkyl halide, is facing. There is this type of base which we call it Lewis base, and then Bronsted base, right? When alkyl halides, when they face a Lewis base, what do? They do a substitution reaction. But instead of Lewis base, if they face Bronsted base, for example, it is a symbolic reaction. Now we will go to the details. When it reacts with a Bronsted base, instead of substitution, what happens? Elimination happens. So basically, when alkyl halides gets in touch with Lewis base, what do? They do this type of reaction, which is called substitution. When they face Bronsted base, then the reaction which is going to happen is called elimination. Now, the next question is, what is Lewis base and what is Bronsted base, in order to predict if substitution is going to happen or elimination is going to happen. So we have a concept of lone pair electron. You remember, carbon has the lone pair of electron. Oxygen has the lone pair of electron. Now, if we start seeing the molecule from that lone pair electron perspective, we are basically working with Lewis acid or base. But instead, if we are talking about not the electron instead, but the proton, then that is when we say we are facing a Bronsted situation, a Bronsted acid or a Bronsted base. So the lone pair of electron can be donated if a molecule or if an atom donates a lone pair of electron. Basically, that is a Lewis base. If another atom that accepts the lone pair of electron, that is basically what we call Lewis acid. And then, when it comes to proton, the donor of the proton is Bronsted acid, and then the acceptor of the proton is Bronsted base. We will give more examples of these specific examples, but before we go to the examples, we will go to the details of substitution and elimination for a while. We have two types of substitution which happens in alkyl halides, and we have two types of eliminations that happen in alkyl halides. The first type of substitution with alkyl halide is called SN2, and the second one is called SN1. The elimination is called E1, elimination 1, E2, elimination 2, and elimination 1. Right? Substitution N2, substitution N1. But what are the full names for these? SN2 basically stands for Biomolecular Nucleophilic Substitution. Well, basically, you read it from the right side. 2 means bimolecular, N means nucleophilic, and S means substitution. Bimolecular nucleophilic substitution is the first type of substitution, 2 substitutions. The second type of substitution is unimolecular nucleophilic substitution. Unimolecular, this one. N stands for nucleophilic, and then S for substitution. And then elimination, E2, again, E stands for bimolecular beta elimination, E1 stands for unimolecular beta elimination. What is the difference between bimolecular and unimolecular? Bimolecular basically means that it is a 2-in-1 process. Bimolecular, 2-in-1 process, 2-in-1 step, which means two reactions happen in the same step. That's why we call it 2-in-1. But as you go to unimolecular, it means one step at a time. There are two steps. The two steps are separated from each other. They are not connected to each other. So, how should I give you an example? For example, if I hit him and at the same time he hits you, this is two steps at one time, at single time. This is called bimolecular reaction. If the first molecule is produced without any delay, the second molecule is produced. But if I hit him, then it takes a while for him, for example, to hit you. This is called two steps, separate steps. So we have those reactions that two steps are happening in the same time. That's why we call it bimolecular. Two molecules are involved. Unimolecular, at first step, one molecule is involved, and the second step, the next molecule is involved. This is true for elimination as well. If we have a two-step elimination, that's called unimolecular beta elimination. If we have one-step elimination, that's called bimolecular beta elimination. If we have one-step substitution, that's called bimolecular, because two molecules act at the same time. That's why we call it one step. If unimolecular means one molecule at a time. First reaction happens with the first molecule when the first molecule products are there, and then the second step of the reaction initiates. So that's why we call it unimolecular nucleophilic substitution. Now, what is nucleophilic? Nucleophilic, basically, we have those atoms or those groups that like the proton, that are thirsty for the proton thirsty, right? So they are electron rich but proton poor. That's what we call nucleophilic. And beta is the secondary carbon. Once we get to the example, we'll talk more about this. So now let's give the SN2 reaction. What basically happens here? A substitution, a bimolecular nucleophilic substitution. It has been symbolized here. We have a hydroxyl group. As you see, it has a negative charge, and it is rich of those pair of electrons. You know, lone pair of electrons, and they want to donate it, right? That's why they are called Lewis base, right? Because they want to donate those lone pair of electrons, Lewis base. If they want to donate proton instead, or accept proton instead, those would be Bronsted base. Lewis base, they give that lone pair of electron, and then Bronsted base, they accept protons. So we have this hydroxyl, and it's called nucleophile. Why nucleophile? Because it is thirsty for the proton. It is rich of electrons. It is reacting to this molecule, CH3Br, methyl bromide. So what happens is here, there are two reactions happening at the same time. This carbon wants to get rid of bromine because bromine is, although they have a bond, but they, as you know, because of bromine is the 7th group halogen, they have the high tendency to grab the pair of electrons closer to themselves. That's why there is a thirst for electron in carbon, which is best fulfilled by hydroxyl group by all these free electrons instead of the bromine. So bromine, the moment carbon shows its readiness to accept the electron from this nucleophile molecule, the group, at the same time, bromine is fast enough to carry out the second step of the reaction and take the electron and release out of this bond. So two reactions are happening at the very exact time. That's why we call it 2S2, which means bimolecular nucleophilic substitution. Bromine gets substituted by the hydroxyl group in a 2-in-1 type of reaction. Both reactions happen at the very exact same time. A nucleophile, which is full of electrons, needs that proton. An electrophile, which is poor electron-wise, and then it shows affinity to the electron, which is shown by the hydroxyl group. Why? Because bromine is unfair in this bond. It has the tendency to take the electron, the pair of electrons much closer to itself. That's why it's fragile, it breaks. Now, characteristics of the SN2 or bimolecular nucleophilic substitution reaction. Here we have S2 bromobutane. We have S2 bromobutane because of 4 carbons, 1, 2, 3, 4, and the second carbon we have bromine. That's why it's called S2 bromobutane. Now this is an alkyl halide, right? So this alkyl halide is exposed to this type of molecule which we talked about, which is a nucleophile, which is rich of electron rich. Now this electron rich compound shows a tendency higher than bromine to share the pair of electron with carbon, so that's why carbon is interested to make a bond with hydroxyl group instead of bromine, and then bromine is broken. This is the transition state. It has the carbon has a semi type of bond under formation, under construction with hydroxyl, and a bond under breaking process with bromine. So it is bonded by dots, that's why. Partially negative charge on this, partially negative charge on this. This is a transition state, and then it breaks down, the hydroxyl group substitutes the bromine. So bimolecular nucleophilic substitution. There is a substitution. Why? Because bromine leaves, hydroxyl group comes. Is when the bromine is detached from the